So we did elaborate on this last week several times. If you have a transfer function, GS, okay, if you are given a transfer function GS in the exam, alright, the first thing you need to ask yourself is whether this is open loop or closed loop. So, take for instance, right? It's an exam question. Okay, so in this question, you can see that part B, an automatic system, blah 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 blah. The commercial greenhouse is designed to maintain relativity and optimum value. Okay, and the system and controller can be modeled as one, which has a normalized open loop transfer function. Okay, so you are given GS, and they tell you that it's an open loop transfer function. Alright? Okay, so you have to be careful on, if you are given a GS transfer function, is it open loop or is it closed loop? Alright? Okay, so if it's open loop, okay, if it's open loop, this will be, output will be Y, and the input, harmony term, U. Okay, U is also a controller output. Alright, so you just say that GU has input US or output. Alright, and I was just saying, okay, any transfer function is just a fraction of output. Alright? And you notice that these are all in all polynomials of S. Okay? So since it's a polynomial of S, alright, generally speaking, you can define this polynomial as any arbitrary polynomial, right? That is applicable for all systems of any order. Alright, so we say that GS is BS over AS. Alright, and we realized last lecture that if you want to look at the stability of the system, okay, the one thing that you can look at are the poles of the system, right? Because the poles of the system will tell you whether the system is going to be stable or unstable. Okay, so take for instance an example. Alright, if you have a first order system, y over s plus a. Okay, we do not pay so much attention to the zero because very often the zeros are always true, or there's no zero. Okay, so if you look at the pole over here, obviously how do you check the pole? The poles will just be the denominator equated to 0. Okay, and then the pole is s equals to minus a. All right, and if a is totally positive, okay. This, if you mark it on the complex plane, it's here. Alright, which is stable. And how do you know that it's stable? Because you do this, and you say that if US is an impulse function, okay, the plus transform is 1. What is your Y? Your YS? It's just 1 over S plus A. Your YT, just e power minus a. Okay? So when t tends to infinity, y tends to 0. Alright? And that's stable. Okay? So you can tell that a system is stable, an open loop like this, whether it's stable or unstable, just by looking at the denominator. Okay? So, E it's not a first order system, but you are given a denominator AS. How do you check for the poles? Poles will just be the solution of AS equals to 0. Okay? And we call this the characteristic equation. Alright, so from now on, especially when we talk about control systems, very often we will tell you, just find where are the poles. Okay, the poles are just the characteristic equation. which is the denominator equated to 0, and solve for s. Alright? So it tells you that this characteristic gradient is very important, obviously, yeah? Okay? So hence, alright, there have been research done on this, and we tell you that if you have a first and second order system, here as shown in the lecture notes, alright, we require that coefficients of AS, which are A0, A1, A2, A3, and etc., the coefficients must be positive. Alright? Okay? All coefficients must be positive, meaning all AI must be bigger than 0. Okay? And for third order systems, alright, the same condition apply, all AI must be bigger than 0, and in addition, okay, there's a certain condition here, and there's a typo, so change that. Alright, the second condition is A1, A2, the product of A1 times A2 must be greater than the product of A0 times A3. Okay? And for any higher order system, alright, we require all coefficients to be positive, and we need to form a Routh array, okay, and check that the elements of the first column in the Routh array are all positive. Alright? So these are the three basic conditions for first and second order systems, third order systems, and any higher order systems. Okay? We'll be going through some examples in each of these categories so you sort of understand how to actually apply these conditions. Okay? Any questions for now? No? Alright? Okay, so you have a lot of text here that tells you what the Routh array is, you know, and how to form a Routh array and so forth. Okay. We'll not read too much into this, but let me just roughly go through some parts of it. So what do you do for higher order systems? First, okay, we need to form a Routh array. And this is only required for higher order systems, meaning systems that are fourth order or higher. Okay? Because for third order, you can just check these two conditions. Right? So for third order system, we do not need to form a Routh array. It's only for systems of order 4. Alright, and how do you form a Routh array? Okay, if you have a system of order n, alright, the array is set out of n plus 1 rows. Why n plus 1? Because, for instance, if n is 5, alright, so you have a row for s to the power 5, a row for s to the power 4, a row for s to the power 3, s to the power 2, s, and another row for s to the power 0. Okay, so we need one last row for s to the power 0. Alright, so altogether there's 1, 2, 3, 4, 5, 6 rows. Okay? Alright, n plus 1. Okay, so this is how you draw a Routh array. Okay, and obviously, the next thing you do is you populate the first two rows. Alright? So how do you populate the first two rows? What you do is you have e to the power 5, e to the power 3, e to the power 1, e to the power 4, e to the power 2, e to the power 7. Okay? And next, there are so many empty rows here, right? So you have to try to fill that in. Okay, I do not know how well I can follow this, but if you just look at this particular row blank here, I'll be going through this in a lot of detail. Okay, but let's just cover what you see. Alright? So how do you come up with this? Just take a to the power 4 times a to the power 3 minus a to the power a4 times a3 minus a5 times a2 over a4. Okay? Checking your head. Alright. Forget about forget about it. Difficult to read. Okay, so as I was saying, okay, S about 5, S about 4, S about 3, S squared, S about 3. Okay, all right, then you start to fill your coefficients. A5, A3, A1, A4, A2, A3. Okay, and how do you fill this element here? This element is A4 times A3 minus A5 times A2 over A4. Okay, and this one, we take A4 times A1 minus A5 times A0 over A4. Okay, this one. On the third row. Got this? Yeah? Okay, next. Alright, so just now, use A4, right? Yeah? So A4 times A3 minus A5 times A2 over A4. And you take A4 times A1 minus A5 times A0 over A4. Okay, now you take this. Okay? So you take this times A2. Alright, minus A4 times this over. Okay? Alright, A2 over A4 minus A4, A1, okay, and obviously, next, alright, you take this times A0 minus nothing over this, okay? So I shall draw my columns wider. Alright, so A4, A3, A5, A3, times A0, A4. Okay, then don't forget to divide. A4, A3, A5, A3, A4. And then you carry on. Okay? I'm not going to do the carry on, alright? But you get the idea. Yes? Yeah? Okay. So let's move on. Okay, we'll start with some simple examples. Oh, you need a copy. You don't have to, it's in your notes. I'm just going through the motion. Okay. Now, are you ready to continue? Yeah? 3.2.2, simple, second order. Okay, what you are given, you have a system. A system with unity, negative, feedback. Alright, so I hope you guys still remember what's unity negative. Cover that last time. It's any system, closed loop, whereby the feedback path is a unity gain, and it's negative. Okay? So for those for those who are looking at me not knowing what I'm talking about, this is a unity negative. Okay? Anything that's a feedback path of a unity gain, so there's nothing, it's a gain of 1. Okay? So unity negative. Alright? A system with unity negative feedback has a forward path transfer function given by G equals to this. Okay? This is not just G. There's a controller transfer function. Okay, and the controller is a proportional gain controller K. Alright, and K is just a real number. Alright, so K could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Nobody knows what K is. Okay, but given that GS now, the open loop forward transfer function is actually of K and original G for the plant. And so this K S plus 1 over S plus 2. Okay, and what do you need to do? First step, obviously, form the closed loop transfer function. Okay? Because we are interested in finding now the range of K for which the closed loop is stable. Okay, so Routh-Hurwitz stability criterion is a stability analysis tool, okay, which can find a range of K, a range of controller A, for which the closed loop system will be stable. Alright, so I have told you the last lecture that to form a closed loop transfer function, just Kg over 1 plus Kg. You still remember this? Yeah? Okay? So just take this, which is Kg over 1 plus Kg. Alright? And then you simplify. Okay, once you simplify this, you end up with K S plus 1 over S squared plus 2 plus KS plus K. Okay? This is your closed loop transfer function. Next, anything about stability. Look at the numerator or denominator. Okay? And the denominator will use a general term A bracket S to define denominator. So AS is just S squared plus 2 plus A bracket S plus K. So this is also called your characteristic equation. Okay? And now obviously you have got coefficients, right? A0, A1, A2. Yes? Okay? The second order system, the stability criterion is all coefficients must be positive, right? So here you say the requirement for stability is that each of the coefficients of the denominator is positive. So what you need to ensure, you ensure that A0 is bigger than 0, K must be bigger than 0, okay? And A1 must be bigger than 0, so S plus K bigger than 0. Okay, you move the 2 onto the other side, so K must be bigger than minus 2. Alright, for those students who are not so comfortable with working with inequalities, please make sure you practice. Because all students can get to this point and then some will give me a wrong answer. Surprisingly, okay? But don't do that. Alright, and then we need to compare these two to tell me the final answer, right? So this says K must be bigger than minus 2. This says K must be bigger than 0. If I need to satisfy both conditions, my final answer is K must be greater than 0. Okay? And this is the final restriction which guarantees that I meet both conditions. Alright, and that's the answer. So for closed loop stability, for this particular system, K must be bigger than 0. Okay? Any questions? Alright? So we move on. What about third order example? Okay, same thing. You are given your kg. Yeah. It's obviously third order, right? Because if you look at the denominator, it's s times s plus 2 by x squared. So you end up with s cubed. Okay? First step, one circle. First step, you form your closed loop transfer function. So as we said last lecture, closed loop transfer function is just ag over 1 plus ag. Okay? And this is only valid for unity negative feedback. Unity does nothing. Alright, so just put in kg over 1 plus kg. Simplify. And you get here. Hopefully you get here. Alright? So be very, very, very okay with your simplifications. Alright, you end up k bracket s plus n over s cubed plus 4s squared plus 4 plus a bracket s plus n. Alright, so same here. To look at stability, you look at the denominator. Alright, the characteristic equation, AS, is your denominator over here. Okay, then next, bring out your Routh-Hurwitz stability criteria for third order. What are the conditions? Two conditions. First one, all coefficients must be positive. Second condition, A1, A2 must be greater than A0, A3. Okay, so there's no typo. Alright? Okay, so check the conditions one by one. Work out what is your A0, A1, etc. So your A0, let's just look at A0. A0 must be bigger than 0. So A0 is 10k. 10k bigger than 0, meaning k must be bigger than 0. A1 greater than 0. A1 is 4 plus k. So 4 plus k greater than 0 implies that k must be greater than minus 4. And the last, and you don't check 4, right? Because obviously A2, which is 4, is bigger than 0. Okay, and A3, which is 1, is also bigger than 0. So there's nothing to check over there. Okay, move on to the second condition. A1, A2 greater than A0, A3. Alright? A1 is 4 plus k. A2 is 4. Okay, so 4 times 4 plus k must be bigger than A0, A3. A0 is 10k, and A3 is, what's A3? 1. Okay? So 4 times 4 plus k must be bigger than 10k times 1. Alright? And then you simplify. Okay, and you get k less than a over 3. Alright? Once you have obtained these inequalities, work out the final answer. Okay, I hope you guys can do this. Or otherwise, I shouldn't be teaching you this, but anyway. This is something that probably you already covered in secondary school, right? No? Okay, yay! Don't get too excited, okay? Okay, I get what you mean. Alright, so you have 1, 2, 3 inequalities. Minus 4, 0, and 8 over 3. Yes? Okay? So k must be greater than minus 4. It's 1. K must be greater than 0. It's another 1. And then k must be lesser than 8 over 3. Alright? Just find a solution that will satisfy all three conditions. Okay? And the solution lies here. Alright? So k must be this. Okay? To satisfy all three conditions. Alright? Okay? Any questions? Anybody cannot see this? let's move on. Okay. All right. For further example, this is when you need to form your group array. Why so funny? Okay. Are you guys ready to continue? Yes? Alright. Same here, a system with unity negative feedback has a forward path transfer function given by this. Alright, so this is your AG. The question is often always asked in this manner. Okay, so what you'll be asked in the exam, if this comes out, is that determine the range of K for which the closed loop system is stable. Okay? So once you see this, it tells you that you do this. First of all, form the closed loop transfer function. While unity negative feedback is just Kg over 1 plus Kg, simplify in that here. Alright, check there is fourth order on the denominator. Okay, and then check for stability. Alright, so here it tells you that AS, the denominator is F power 4 plus 6S cubed plus 11S squared plus bracket 6 plus 8S plus 9. Alright, this is a fourth order system. Okay, so the conditions are all the coefficients must be positive, and in addition, okay, elements in the first column of the group array must all be positive. Okay, so these two. So how do you check coefficients? All coefficients will be positive. First of all, it means that 5k must be greater than 0, right? Yeah, so k must be bigger than 0. 6 plus k must be greater than 0. So k must be greater than minus 6. Alright? And in conclusion, meaning k must be greater than 0. Next, you form the root array. Okay? S power 4, S to the power 3, S to the power 2, S to the power 1. All the way to S power 0. Okay? Next, you fill your coefficients. So this A4, which is 1. A3 down here, 6. A2 is 11. A1 is 8 plus 6. A0 is 5k, and then nothing. Okay? You look on the next row. Before you look at so next row, and will tell me what's the next row. You look at 6. Alright, you take 6 times 11 minus 1 times 8 plus 6 divided by 6. Okay? So you got here 16 minus k over 6. Just simplify. The next element, alright, you still look at 6. You take 6 times 5k minus 1 times nothing over 6. So you end up with 5k. Okay? Carry on. You look at 16 minus k over 6. So you take 16 minus k over 6 times 8 plus 6 minus 6 times 5k divided by 60 minus k over 6. Simplify, you know this. And then nothing. Okay? And then for S power 0, you write 5k. Alright? Okay, other also check that we take this, blah, 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 times 5k minus 60 minus k over 6 times nothing, divided by itself, then I'm finding it. Okay, in any case, this is always a zero. Alright, so can you work this out, the root array? Yeah? Okay, so once you have the root array, check the conditions. Okay, we covered A1 and A0 just now. Then look at the root array. First column. Okay, so column 1, row 3 must be greater than 0. So 60 minus k over 6 must be bigger than 0. 60 minus k bigger than 0, k must be less than 60. Anybody who doesn't know why 60 minus k greater than 0 means k must be less than 60? You know? The one in the SIP t-shirt. Is this okay? No, not okay. Okay, you ought to know this, huh? Well, because this is very important to the course, let's just look at it. Okay. You want me to go through this? Yes? Okay, alright. So we have gone through A0 bigger than 0, we have gone through A1 bigger than 0, and this 2 tells you that k must be bigger than 0. Okay, now we look at the root array. We look at column 1, row 3. Column 1, row 3 is 60 minus k over 6. Okay. Okay, so this implies that 60 minus k must be this. Okay, you can bring your k to the other side. Okay, so you can see that k must be greater than 60. Is that correct? Is this correct? Yeah, we're busting Johnny infinity, right? Are you guys still awake? No. Let's finish this example and go for right? Okay, so k must be less than 60. Yeah? Next row. Okay? You want me to go through this?
Yes.
Yes, so can you please keep quiet because I can't focus with all this mumbling. Alright? So next row you have minus k squared plus 4k plus 360 minus 180k over 60 minus k. Okay, and this must be bigger than 0. Alright? So how do you work this out? When you have something like this. First of all, obviously you simplify what's on top, right? So this gives you minus k squared minus 126k plus 360 over 60 minus k bigger than 0. Okay, you have a denominator over here. What do you do with it? Huh? Can you just remove it? By multiplying, right? By 60 minus k. But will this change the sign? No, but only if 60 minus k is positive. Okay? Is 60 minus k positive? Only if this is true, right? Only if k is less than 60. Okay, but since we say that we have to satisfy k less than 60, so the denominator here will be positive. Okay, so you can just multiply by 60 minus k. Alright, so the inequality sign will not change. Okay, so you end up with minus k squared minus 126k plus 360 greater than 0. Okay? Alright, now that you have this, next, how do you solve this? Okay, first you look at the quadratic equation. Look at this first. Okay? Alright, and the roots are just minus b plus minus square root b squared minus 4ac over 2a. Okay? And what do I have to take? Huh? Okay? So solve this. Then how is this? So end up minus 128.8 or 2.79. Okay? Alright? So when would this quadratic equation be bigger than 0? When k is minus 130, or when k is minus 120. Okay, maybe you don't know. So what you do now is this. Put in these two numbers. Okay, pick out a calculator. Alright, punch in any number. So let's say we punch in 3. Alright, you end up with minus 9 minus 378 plus 360. Okay? So that is negative, so right? Okay, so it must be here. This way. Okay? You can also check out this part. I don't have a calculator, but you do. Alright, so I just checked 3 is not supposed to be here, so this is out of the question. Alright, so just to conclude, alright, just now you already said that k must be bigger than 0, so at least here. So we can say that the range of k must be between 0 and 2.79. Got this? Okay, without fail, in every year, students cannot get here. And I hope this year will be an exception, right? Okay, we'll take a 10 minutes break. We'll come back at 12 o'clock. For those who cannot get this, please calm down and I'll explain to you. Alright?